Expression for average velocity. Again, we consider a figure in which a particle is moving in a two coordinate axis, or I can say is moving in a plane. Now, this particle is at a time t. Okay, I mean this particle is at a point p when the time is small t. When the time is small t, the particle is at point p, and when the time is t dash, the particle is lying at a point p dash. Okay, so as the particle change its position from p to p dash, then we say that this particle has cover a displacement, and the displacement, as you know, has a magnitude as well as direction. So the magnitude of displacement in this case is from p to p dash, right? This is the magnitude. The length of this line stands for the magnitude of the displacement, and the direction is from p to p dash. And for the displacement, we write delta r arrow. Okay, next, let us come to average velocity. If v bar is the average velocity, then we define average velocity as the ratio between the displacement and the time interval. Now this time interval delta t is equals to the final time minus initial time. Your final time it is t dash, your initial is t. So this is the time interval. Now if this is the average velocity, then I can say this v bar is equals to, in terms of rectangular component, I can say this is equals to delta. Instead of r arrow, I can write xi plus yj upon delta t, isn't it? Or v bar is equals to delta xi plus delta yj upon delta t. Now, if you split this delta t, then you will get delta xi upon delta t plus delta yj upon delta t, or v bar is equals to, what is this delta x upon delta t? This is the change in the displacement upon change in time, and the displacement here is along x-axis, so we get the velocity along x-axis. And so instead of delta x upon delta t, we write vx. Similarly, in place of delta y upon delta t, I will write vy. Okay, so this is your expression for the average velocity of a particle moving in the xy plane in terms of rectangular component vx and vy. Okay, now when you look at this equation, if you look at this equation, we see v is equals to delta r upon delta t. So because this delta r is a vector quantity, so the directions of this average velocity is determined by delta r. If delta r is acting from p to p dash, it means the directions of average velocity also will be along, right, from p to p dash. Okay, next is instantaneous velocity. You know, instantaneous velocity is defined as the limiting value of the average velocity when the time interval tends to 0. That is, the instantaneous velocity v arrow is equals to limit delta t tends to 0 of delta r upon delta t. And for this we write dr arrow upon dt. This is the mathematical expressions of instantaneous velocity. Now to understand about the directions of the instantaneous velocity, let us consider these three figures here. In this figure A, what do we see? We see that the particle is at a point P, when the time is t, and at a point P1 when the time is T1. I'll repeat, the particle is at a point P when the time is small t, and as the time is going on, then it reached this point P1 at a time T1. So the time interval in this case, let's say, is equals to delta T1, which means final time T1 minus initial time T. So this is the time interval and this is the displacement. So with this displacement, delta R1, let's say delta R1 is the displacement of the particle from P to P1. Then where is the directions of the average velocity? So we have seen in the right just now that the directions of the average velocity is parallel or is along the same as the directions of the displacement vector. Now coming to figure B, the particle is at a point P when the time is small t, and it is a point P2 when the time is T2. So in time interval delta T2, then the particle change its positions from P to P2 and it cover a displacement delta R2. So this is the directions of delta R2, and so the directions of average velocity also should be parallel to this displacement vector delta R2. Okay, so please note down here that this delta T1 is more than delta T2. Okay, next, coming to figure C. In this figure C, we have considered that the time interval delta t is tending to be 0. So when the time interval is so small, just look at this point. This point, the final point, right, will be very close to the initial point. Okay, I'll repeat. When the time interval between any 2 points, it is, when the time interval it is so small, which is almost tends to 0, then the final point will lie almost at the same location of the initial point. So in that case, this final point, if this is my initial point, then my final point also will be almost here. So at this point, this displacement line, it becomes like a tangent in this way. Okay, so this tangent now, it represents what? The directions of the velocity at this point. Alright, so this directions of velocity at this point here, it is not the directions of the average velocity, but it represents the directions of the instantaneous velocity. Why? Because the time interval is almost equals to 0. So please note down, when the time interval is almost equals to 0 or tends to 0, then the directions of the instantaneous velocity is equals to the tangent at that point, right, on the curve. Okay. Velocity in terms of rectangular components. So we have seen that the definitions of, the mathematical expressions of the instantaneous velocity is written as v equal dr rho upon dt, or v rho is equals to limit delta t tends to 0 of delta r rho upon delta t, or v rho is equals to limit delta t tends to 0. In place of delta r, I will write delta xi plus delta yg upon delta t. Now, if you split this delta t, then you will get delta x upon delta t plus delta y upon delta t. Okay, this is a bracket here. Okay, next you take the limit on each term. That is, when you remove the bracket, then you have to take the limit for this and for the second term. So taking limit delta t tends to 0 of x upon delta t, you get like this, plus limit delta t tends to 0, delta y upon delta t times j cap. Or we can say v arrow is equals to, now this limit of delta t tends to 0 about delta x upon delta t, this would mean the instantaneous velocity along x-axis. So for that we write vx. Okay, sorry, this I cap should be outside, okay, because it tells the directions of the velocity along x-axis. Plus, similarly, for this limit delta t tends to 0 of delta y upon delta t, I will write as vy, which is the velocity along y-axis, and we have j cap. Okay, so v arrow equal vxi plus vyj is the expressions of the instantaneous velocity in terms of rectangular components. Okay, now when you look at this figure, let's say this curve here represents the path along which the particle is moving. Suppose at any instant of time, let's say at this time, the point is P. At this time, or at this point, where is the directions of the instantaneous velocity? The direction, it should be tangent along this point. So this is the directions of the instantaneous velocity v. Now we resolve this instantaneous velocity v into two rectangular components, vx and vy. So for that we have to do like this. Okay, suppose this line here, it is the component of v along x-axis, so we write vx, and this vertical is the component of this v along y-axis, so we write vy. Okay, and let us say that the instantaneous velocity v makes an angle theta with respect to the horizontal or with respect to the x-axis. Then we can say that the magnitude v, as we have seen before in the rectangular component, right, of a vector, this v can be written as the magnitude of this. When I say v, it means the magnitude of the instantaneous velocity. Let me just write here. Magnitude of instantaneous velocity is v equal vx square plus vy square. This is the magnitude of the instantaneous velocity. Similarly, about the direction, to know the directions of this v, we take tan theta. So tan theta in this triangle is equals to vy upon vx. So by knowing the velocity component, then you will know theta, and by knowing theta, you know the directions of the instantaneous velocity at any given point of the path along which the particle is moving.